Hello everyone, I am Omkar Shavale from TY Electrical B. So I am going to present a presentation on switch reluctance motor. So we are seeing a diagram of switch reluctance motor which is in real. So switch reluctance motor is a motor which is also called as an SRM motor, where it is an electric motor in which torque is produced by the tendency of its movable part to move a position where the inductance of excited winding is maximized. So an SRM is a type of synchronous machine. It has wound field coils of DC motor for its stator windings and has no coils or magnets on its rotor. So it can see that both the stator have silent poles, hence the machine is doubly silent, singly excited machine. So the stator windings on the diametrical opposites are connected in the series or parallel to form one phase of the motor. So we can see the diagrams of 6 by 4 pole and 8 by 6 pole, where the 6 is the stator poles and 4 are the rotor poles. And also for the next diagram, the 8 are the stator poles and 4 are the rotor poles. So there are various several combinations like 6 by 4, 8 by 4, and 10 by 6. So the configuration with higher number of stator by rotor pole combinations have less torque ripple. So there are two types, the radial field and the axial SRM. In the radial field SRM, the magnetic field path is perpendicular to the shaft or the along the radius of cylindrical stator and rotor. So we can see the diagram of this SRM radial field and the short flux path in 5-phase radial field SRM with 10 by 8 pole as shown in the diagram. There we can see the A, B, C, D, E, and also there is the axial field SRM. The magnetic field path is along the axial direction, means the magnetic field is flowing through the axial direction, where we can see the diagram of the motor, means whole motor, where the rotor is and the stator are connected to it, where the second diagram we can show a rotor diagram, and the third one is the short magnetic flux path, where the magnetic flux are producing in axial direction to the rotor. Then the principal operation of SRM motor is show where the cross-sectional model of three-phase SRM winding and equilibrium position with phase 1 excited. As first we can see the stator and rotor where the windings are wounded to the rotor. As second diagram we can see the rotor, the poles are wounded with three phases supply where switches are connected, and the third diagram where we can see that opposite poles are attracted toward each other and produces a magnetic field in the rotor. And the rotor rotation as switching sequence proceeds in three-phase SRM. The rotor direction is opposite to the direction of excited phase. The switching angle for the phase current is controlled and synchronized with the rotor position, usually by means of shaft position sensor. So now we are going to see the torque production. As the we can see to the y-axis we can see the flux linkage, and to the x-axis we can see the current. Where we can see the stored field energy and the co-energy. Where between stored energy and co-energy the magnetization curve is formed. So the torque production in SRM can be explained by using the elementary principle of electromechanical energy conversion. The general expression for the torque produced by one phase at any rotor position is so T is equal to del W upon delta, where I is equal to constant, where T is the torque, W is the co-energy, and delta theta is the displacement of the rotor, where formula is T is equal to dw upon d theta, where I is constant. The constant current constant in the formula ensures that during such displacement, the mechanical work done is exactly equal to the change in the co-energy. The torque production in a motor with no magnetic saturation, the magnetization curve would be straight lines. At any position, the co-energy and the stored magnetic energy are equal, which can be given as Wf is equal to W dash is equal to half of Li square, where L is the inductance of a exciting stator phase at a particular position. In this case, the instantaneous torque can be derived as T is equal to 1 upon 2 I square into dl by d theta. So the energy conversion process in the real switch reluctance motor, the energy conversion process in an SRM can be evaluated by using the power balance ratio. As we can see the formula given, the first term represents the stator winding loss and the second term denotes the rate of change of magnetic stored energy. The third term is the mechanical output power, and the second term always exceeds the third term. The most effective use of the energy supplied is to maintain phase current constant during the positive dLph divided by d theta slope, in which way the second term is equal to 0. So now the torque speed characteristics are shown in the diagram. The torque speed plane of SRM can be divided into three types of region: the constant torque region, constant power region, and constant power speed region, where we can see it in the whole diagram. So now this is the block diagram of an SRM drive system where we can provide DC supply, which we invert and can convert it the DC to AC, which we can give to this motor, switch reluctance motor, where the position sensor is connected to the motor, where it is given to the logic circuit, and then the logic circuitry is connected back to the inverter. So the position sensors we used are phototransistor and photodiodes, Hall elements, magnetic sensors, pulse encoders, variable differential transformers. So these are the applications of SRA motor. So first one is the flame-proof system for potential explosive atmosphere, washing machines. It is an environmentally friendly air conditioning system for passenger trains and servo systems for advanced technology weaving machine. Thank you.